Hello everybody, so if I pass out, don't worry, I think I'll come to a reasonable amount of time. Don't let me miss my next class though. Alright, so yesterday and the previous lecture we learned about the sum rule, being able to pull out constants, the product rule, quotient rule, the chain rule, all these rules. So today we're just going to work examples. Get used to using all these rules. I know, you go to college to avoid having to follow rules. In calculus and math in general, you break the rules and you get in trouble. Okay, so let's just start easy. Let's find, say, the derivative. Just a good easy function. X squared. Okay. X squared times 3x cubed plus 2 to the 5x plus 3. Good easy function to start us off. Okay. So let's be very careful with this, so we make sure we're following the rules. So what's going on? Well, okay, this is way too nasty. Okay, we don't know how to do this. Okay, so you have to say, I don't know how to do this. Why don't I know how to do this? We haven't learned it yet. We have a variable and an exponent. And none of our rules talk about what to do when you have a variable and an exponent. Okay. Let's make the problem even easier. Say my function is y equals x to the x. And I want to know what is dy dx. Well, if you apply the power rule to this, then you say, oh, well, clearly this is x times x to the x minus 1, which is x to the x. Right? Okay, so the answer is no. This is not right. And why? Well, the power rule was not defining a function like this. You didn't have a variable as an exponent. You had a constant as an exponent. Okay. So we can't use the power rule here. This is no good. Later on, we're going to see how to handle this sort of problem. But right now, we don't know how to solve it. Okay. Which means we can't solve this one. Okay, so we have to make this easier. Okay, so let's just put a 5 there. That's easier. Okay, so now what can we do? Well, we have two functions. Okay, and we've multiplied them together. Okay, so it's a product of functions. So what rule do you think we have to use? The product rule. Okay, and what does that say? Well, it says that you can first just write down the first function times the derivative of the second function plus the second function times the derivative of the first function. Okay. So, x squared, that's really easy. You don't do anything to it. It's x squared. Derivative of this. What do we have to use on this one?
Chain rule.
We have to use the chain rule, right? Why? Well, I have a composition of functions. I have an inside function and an outside function. Okay, so let's recall what the chain rule says. The chain rule says if I have two functions and I compose them, then I'm going to get, and I take the derivative, then I get f prime composed with g times g prime. So I'll rewrite my x squared, and then what am I going to get here? Let's see. So I have to take the derivative of the outside function. Okay, so I just have some blah. I don't worry about what it is. I just know it's a function, something to the fifth. Okay, say x to the fifth. And the derivative of that using the power rule is 5 whatever to the fourth. But then whatever that is, I have to replace with 3x cubed plus 2. That's what the composed with g means. So I get times 5, and I put this in, 3x cubed plus 2 raised to the fourth. Times, you can't forget the times, right? Because I have to multiply it by the derivative of that inside junk. Okay, so what's the derivative of this? 9x squared. Okay. 9x squared. Plus, okay, now this part stays the same. And then the derivative of x squared is
2x.
Okay, and so then you can simplify this in any way you want to. I'm not so interested in doing that. Okay, I mean, from now there's no more calculus involved. It's just algebra. Okay. Is that easy enough? Right? So we used, well, almost all of our rules. We didn't use the quotient rule, right? We used the product rule to evaluate this, because it's a product. We used the chain rule to evaluate this. It was a composition of functions. We used the sum rule, right? Because actually to find the derivative of 3x cubed plus 2, okay, which is this guy, okay, we actually do the derivative of this plus the derivative of that. And we use the power rule every time we wanted to find some derivative of something to the square or something to the fifth. Okay, no problem. Okay, let's use the chain rule to prove something interesting. All right, so we know that the power rule works for integers. Okay, we started off just proving it for natural numbers and 0, and then we were able to prove it using the chain rule. We were able to prove it for, or rather, I don't know, I can't remember if we used the chain rule or the quotient rule yesterday. In any case, we know that it works for all integers. What about for fractions? What do you think? It's the power rule. Does the power rule work for fractions? So, for instance, if I have y equals x to the p over q, is, so this is just a fraction, is dy dx equal to p over q times x to the p over q minus 1. Okay, that's what the power rule would say for fractions. So is this true? What's that?
Maybe we can test it by using the limit.
Oh, we can test it using the limit. Okay, that's a good idea, although we're not going to do that. Right. Why are we going to do that? Well, because we're trying to avoid limits as much as possible, right? Well, let's see. Let's start again with y equals x to the p over q. Okay, so here, I just, so we're clear, p and q are integers, and of course q is not 0, because I don't want to divide by 0. Okay, so this fraction is annoying. So how could I get rid of that fraction? Okay, I could always turn it into a decimal, but I'm no happier with decimals, and frankly, taking p over q, which is a perfectly legitimate fraction, and trying to find a decimal that corresponds to it is...
The square root, and then that's the
You need the key root
cube
Next
root,
to the
square root, and cube.
Okay, so what you're saying, this means do the qth root and then raise to the power of p, right? Okay, so could I get rid of this, if I wanted to somehow get rid of this over q business, could I do something to this side of the equation to solve it? I mean, here I've taken a qth root, and that's why I get this fraction. How could I get rid of a qth root?
Q, like raise it to a Q.
Raise it to the q, right? Okay, so if I raise one side to the q, I have to raise both sides to the q. And of course, the reason we did this is because that's now x to the p. Okay, fine. I'd like to take a derivative. So I'm going to take a derivative of both sides. Okay, the right side is very easy. It's just the power rule. Right? Derivative of x to the p is just px to the p minus 1. What do we do with the other side? Well, remember, y is a function of x. And now I have some function and I raise it to the qth power. So this is really a chain rule situation. I have a function and I've composed it with another function. One of the functions is y, and one of the functions is x to the q. So the chain rule says that I have to do two things. I have to pretend that, okay, forget about it's just a blah, and I take the derivative, okay, which becomes q blah to the q minus 1. And blah is y, times the derivative of the blah. Okay, well the derivative of the blah is just dy dx. It's just the derivative of y. So qy to the q minus 1 times dy dx equals px to the p minus 1. Okay, let's just solve for dy dx, because that's what we were looking for. Okay, so dy dx is equal to this divided by this term. Okay, but that y, I don't really want a y in my answer, do I? I'd really like to just get all x's. But I know what y is. Y is x to the p over q. So let's see, this p over q, let me pull that out. And then I get x to the p minus 1 over, well, let's see, I have x to the p over q, that's the y, and I raise it to the q minus 1. Okay, so now I just need to use all my rules of exponents to figure out what this is. All right, so first I can multiply. Right? This becomes this thing times this thing. And then what happens if you have a fraction, x to a over x to the b? How does that simplify? Yeah, you subtract. It becomes x to the a minus b. So this is x to the p minus 1 minus, okay, so I can rewrite this as p times q minus 1 over q. Oh my gosh. Boy, that looks bad, huh? Okay, so, well, let's see if we can simplify that a little bit. Okay, so let's just forget about the x. Just write p minus 1 minus p times q minus 1 over q. Okay, well, I'd like to make this one fraction. So I'll multiply by q over q. And now I can subtract these two. So let's see, the bottom is going to be q, and the top, let's see, you get pq minus q minus pq minus is plus, p times 1 is p. So plus p. Ah, that's not so bad, right? Because the p and the pq's are going to cancel. So you're left with, let's see, this becomes p minus q over q. And if we split this fraction back up, this is p over q minus q over q, which is p over q minus 1. Oh, cool. So this is, right? Oh, I can't tell me I left out my p over q. Always mind your p's and q's. Okay, so what we've now done is prove the power rule, not just for integers, but for all rational numbers. And so if you have any fraction, we can now use the power rule. So this is kind of cool. You start off, you use this binomial theorem. Okay, that was, a little bit nasty, right? But it was short. And that gives you it for natural numbers in 0. Then you reduce all integers to that case. Okay? And then you take all rational numbers and reduce it to the integer case, which really just comes down to the natural number case. So you've just kind of incrementally built up the whole system, which is nice. And later on, we'll show that it works not just for rational numbers, but for all real numbers. Okay, so let's just point out something that we did along the way. We used the chain rule to attack this side that had a y to the q in it. When you have an equation like this, where you're actually both manipulating the x's and the y's, and you differentiate with respect to x, right? So that in effect you end up using the chain rule on the y side of the equation. This is sometimes called implicit differentiation. So we'll cover that in more detail later, but this was mentioned right here. I'm doing implicit differentiation. But it's just a funny name to hide the fact that you're just using the chain rule. That's all you do. It's just the chain rule. There's nothing different about it. Okay? So this is nice. So let's do an example. It's a very easy one. What is the derivative of the square root of x? Is that the derivative, or is that what the function is?
This function.
That's what the function is. Okay, so if I write it as square root of x, it's hard to see what to do. But if I change this into x to the 1/2, now it's just a power rule problem. So we just saw what you do. You say, okay, 1/2 x to the 1/2 minus 1. And if you want to write this down in square root notation, this becomes 1 over 2 square root of x. All right? Let's do one trickier. Let's find the derivative of, say, x, square root of x plus the square root of x. Could happen. Okay, so what's the first thing I'm going to want to do to this?
Change the square root.
You got to get rid of all those square roots, right? Square root. You think about, radian measure versus degree, square root signs versus 1/2 powers, right? There's just, in each of those pairs, there's one that you should use and one of them that you really shouldn't use, right? should always use radian measure, and as much as you can, you should always use fractional exponents instead of square root signs. It's not what we're taught to do at an early age, but it's what you should do. All right, so let's rewrite this. So this outside square root is going to give me something to the 1/2. And this inside square root is going to give me something to the 1/2. And then this last square root gives me something to the 1/2. All right, is that true, what I wrote? Okay, so this is the square root of x. And this becomes the square root of x plus the square root of x. And this becomes the square root of x plus blah, blah, blah. So up to number of parentheses, I think this is correct. Okay, now what do? How can I simplify? Ah, of course, I just put this 1/2 in everywhere, right? Maybe you're dreaming. Would that be the freshman dream again? Yeah. Okay, so that's our first instinct, right? We do this. We think, oh yeah, that would be so nice if exponents. I just put the x to the 1/2 here and put these 1/2s all together, and things would be so nice, right? No, doesn't work, right? Okay. So remember, if it worked, then we could have done it in the first place when it was square root. We know we can't do that. Okay. So what rule can we use here? Chain rule. Excellent. Excellent. Okay, so we're going to have to use it several times, though. Right? 'Cause there's a lot of inside functions. There's like an onion. You have to keep peeling away at it. All right, so let's look at the outside function. All right, it's something to the 1/2. So you can just have to the 1/2. Okay, so the derivative of to the 1/2 is 1/2 to the negative 1/2. Okay, fine. Times, of course, the derivative of, so this is 1/2 times x plus x to the 1/2, 1/2, and then this all goes to the minus 1/2, times space times the derivative of the in the middle. Okay, so it's everything but this 1/2. So it's this inside chunk. Okay, well that's not bad. This, as nasty as it looks, right? We're done with it basically. There's no derivatives left anymore. So all you have to do is focus on these derivatives. Okay, fine. So let me just call this A, so I don't have to keep writing it. Okay, so this is A times. Now I need the derivative of this sum of functions. So the derivative of the sum is, of course, the sum of the derivative. So first I do the derivative of x. Okay, that's easy. We all know this one, yeah? You can say it very loudly.
Yep.
1.
No, not yet. Yes is not an answer. Yeah, 1, right? Okay. So that's fine. So we get 1 plus. Okay, now we have another function which, oh my goodness, we have another composition of functions. So we're going to have to use the chain rule again. Okay, so we have a new, and what are we going to do with it? So first we do the derivative of blah, and what are we going to get? We get 1/2 x plus x to the 1/2, all raised to the minus 1/2, times the derivative of the in the middle. Okay, fine. This is all good, so let me call this, actually, yeah, we'll just call this B. So I get A times B times Okay, so what do we get here? Well, this is okay. We have a sum of two very easy functions. Okay, derivative of x, well, we already said what it is, it's 1. And the derivative of x to the 1/2, you know what that is. It's 1/2 x to the minus 1/2. Now, it's very likely that if you expanded a and b back out, that you could probably, there's a hope anyway that you could cancel something. But again, this is not calculus anymore, this is algebra. I don't worry about that in this class. Questions? What do you think, Shannon? Are you happy? I mean, not philosophically or in a life version. I have nothing to do with that.
It makes sense.
Yeah? Okay. Could you do this, you think?
If I worked
If you worked hard
hard enough on it.
enough on it. You mean when you work hard enough on it? Okay. Very good. Okay, let's do another one. Let's look at the derivative. Let's say cube root of 3x plus 3 squared times x squared minus 4 to the 1/2 power.
So you're gonna want to change it to that function to the 1/3, and then do the chain rule again.
Okay, so first step is we don't like cube roots. So we'll take all this inside garbage and we'll raise it to the 1/3 power. Okay, that's how we replace cube roots. Fine. What's my next step? The 1/3 out?
I mean, yeah, times the derivative of the,
So you're suggesting that if I have the derivative of something raised to the 1/3, I can move the 1/3 to the front?
and not other. I mean,
So what is true is if this was times 1/3, then I can move it out. But I cannot pull exponents out. Okay. With exponents, I have to use, for instance, the power rule.
I mean, same thing.
I mean, here I did not take the 1/2 out. I actually took the derivative.
This is what I mean.
Okay, so yeah, so I could do the chain rule. Now, there's actually something that you're missing, and you're probably missing it because you're thinking I'm not going to mess up with the freshman dream again. Yeah, look, I have two things multiplied together and I raise them to a power. I have effectively a times b to the m. So I can make this a to the m times b to the m. Right? That is, I can take this 1/3 and move it inside and multiply it by these exponents. So I can avoid the chain rule at least one time. Now, notice if there was a plus here, you couldn't do that. Right? That would be the freshman dream. But here you have multiplications here, okay. So we have 3x plus 3 to the 2/3 times x squared minus 4 to the 1/6. Okay, that's not that bad. Okay, what do I want to use now? What's my next rule?
Power rule? No. Yes. No, product rule.
Product rule, right? I have two functions that are multiplied together. I have to use the product rule. So this says, I can write down the first function. times the derivative of the second function plus, more space is required, okay, the second function times the derivative of the first function. Okay. So this term's great. I don't have to do anything with that. What about the derivative here? What rule am I going to use to compute that derivative? The power rule coupled with the chain rule, right? And I use them both at the same time. Right? The chain rule says, okay, I have some function and it's raised to a power, so I really have a composition of two functions. So I'm going to first find the derivative of this, right? Pretending at the beginning that it's just an x, okay? And then I can use the power rule. Ooh. All right, so we get a 1/6 x squared minus 4 to the lowest 1/6 minus 1.
-5.
-5/6. Times, well, the derivative of the inside, which is x squared minus 4. Right? That's what the chain rule is telling me to do. First, take this derivative and plug that function back in, and then take the derivative of the inside function. Okay? Now the second half, I don't have to touch the first part of it. And let's see, I get, what do I get? Well, again, I'm going to use the power rule and the chain rule at the same time to get 2/3 3x plus 3 to the, okay, 2/3 minus 1 is it 1/3?
-1/3.
Negative 1/3. Times the derivative of the inside, 3x plus 3. Okay, so all of this stuff, not including that, this stuff, not including that, is now done. I mean, it is what it is. Right? The only thing we have to compute are these very simple derivatives. Right? X squared minus 4 and 3x plus 3. So what's the derivative of x squared minus 4? 2x. Right? Power rule tells us that. And what's the derivative of 3x plus 3? 3, right? Okay, it's the derivative of 3x plus the derivative of 3. Derivative of 3 is 0. And derivative of 3x is 3, right? Well, 3x is just a line with slope 3. So, of course, the slope is 3. So this bit is 3. Okay, and certainly there's some simplification that can be done. For instance, this 3 and that 3 are going to cancel. It's just algebra. Okay? I'm not so interested in simplifying all this. And, yeah, there's a little bit of simplification that can be done. Math. I don't care. I want you to know how to take a derivative. Okay? So that's pretty hardcore. Right? There's a lot of functions going on here. Now, later on, when we get trig functions and exponential functions, logarithmic functions, and so forth, I'm going to start giving you chain rule problems with those too. But it's always going to come down to the same idea. Right? You just notice, oh, I have a composition of functions. I use the chain rule, apply it correctly, and it may look a little nasty, but at every step along the way, you just always try to reduce it down to rules that you know, like the power rule and the product rule. Any questions on this one? Or anything else? Okay, let's do one more example, and let's use it to actually compute the slope of a tangent line. In fact, let's even, maybe, if we're lucky, come up with the equation for the tangent line. So let's first find the slope of the tangent line to the curve. What's a good curve? How about 3x squared minus the square root of x over 2x cubed plus 4. And let's look at x equals 1. Okay, so this, this is a pretty hideous function, yeah? And if somebody said draw this function, I'm sure you'd be scrambling for the calculators pretty quickly, right? Okay, later on we'll actually show how to graph things like this, but okay, just assume for now that this is terrifying. Shannon, is it terrifying? Yeah, a little terrifying. Good. Okay, so you have a terrifying function. Somebody says find the equation, or rather the slope of the tangent line at a specific point, right? So first, you can't graph this thing, at least we don't know how to yet. And then to pick a point and look for the tangent line and say what's the slope of that? Ooh, who knows, right? Okay, so let's see how we would attack it. Well, remember, slope of the tangent line. This is just another way of saying derivative. Right? The derivative was defined as the slope of tangent lines. Okay, fine. So we better take a derivative. In fact, just a general rule of thumb in this class. If you don't know what to do, take a derivative. No? There's like probably a 4 in 5 chance that it's the right thing to do at that point. And even if you get it wrong, it's never such bad practice to take a derivative. So it could be the right thing. Okay, so what is dy dx in this case? All right, well, what's the first thing that I want to do when I look at this function? What's that? Yeah, the square root, right? There's no sense in keeping those around. I'll make that a 1 half. But I need to take a derivative. Now, here I have not a product, but a quotient. So what rule am I going to have to use? Quotient rule. Uh-oh. Now I got to remember what the quotient rule says. All right, so it's low d high less high d low. D high d low. Okay. So there was the quotient. So this says I need to take the bottom and multiply it by the derivative of the top. Then I need to subtract the top times the derivative of the bottom. And then I need to take all of that and I need to divide it by the square of the bottom. Okay? Well, this shouldn't be that hard. Okay? There's nothing hard anymore. I'm just going to pull these 3's out and use the power rule. Same thing here. Everything should be pretty safe. Okay, what's the derivative of 3x squared? 6x, right? You can forget about the 3 if you like. Just pull it out. Say the derivative of x squared is 2x. Then we put the 3 back in. You get 3 times 2 is 6x. Right, then, okay, we already saw the derivative of x to the 1 half is minus x. All right, 1 half x to the minus 1 half. So minus 1 half x to the minus 1 half. Minus, okay, we have 3x squared minus x to the half times, okay, the derivative of 2x cubed.
6x squared.
6x squared, right? And forget about the 2. The derivative of this is 3x squared. put the 2 back in, you get 6x squared. Right? Plus the derivative of 4, which is 0. Right? And then all of this over 2x cubed plus 4 squared. Okay, so there may be some things to simplify, but I'm not going to spend any time trying to find it. Now I just want to step back and think, what did I want to do? I wanted to find the slope of the tangent line at x equals 1. Okay? Well, this derivative tells me the slope of the tangent line at any point. And if I want to know where it is when x equals 1, I have to plug x equals 1 in. So the way that you can notate this is you put dy dx, put a vertical line and then say x equals 1 at the bottom. And that says I'm taking the derivative and I'm evaluating it at 1. What is this equal to? Well, plug 1 in. You get 2 plus 4 is 6. 6 minus a half, which is 5 and a half, which is 11 halves. Minus 3 minus a half, which is 5 halves, times 6, over 2 plus 4 is 6, squared is 36. Well, this I will simplify, because I hate to leave numbers unsimplified. Let's see, those cancel, you get 3, so you get 33 minus 30 over 36. Which is 3 over 36, which is 1 over 12. Oh, did I make a mistake?
Yeah.
Oh, what did I do?
3x squared minus x to the power of 1/2. You did x to the power of -1/2. Plug in for that.
Oh, wait, where did I do it?
Second.
The second
Second.
down. You go to the right now.
Second.
A little more to the right.
Yeah, that one.
No, the next one. There, yeah. You plugged in 1 wrong there.
I plugged in 1 wrong here? Oh, I did 3 minus 1 is, should be 2.
Yeah.
And what did I
You
do?
did to the other one
Ah,
too.
I did 1/2, didn't I? 3 minus a half. Yeah, so this should be 3 minus 1 is 2. Is that,
Yeah.
did I do it? Is it correct now?
That's what I got.
And did I do it wrong here too? No, that's correct. 6 minus a half, that's fine. Okay, I think that's 3 minus 1. You look unhappy, and you're smart, so I'm worried. Okay, let's see. Again, this one was 33. Now it's minus 12 over 36. And 33 minus 12 is 21. 21 over 36, same as 7 over 12. Now, that's actually, to me, surprising that you get this answer. And I'll tell you why I'm surprised. It's probably because we chose x equals 1 that we actually get a rational number. I mean, I'm a little surprised. I mean, you think about it, you have this really weird function doing all sorts of weird things, and you look at the slope of the tangent line at x equals 1. What are the odds you even get a rational number? Right? I mean, most of the time, if you take a slope, it should be, well, it's always a real number. But if you just choose a random slope, well, most random numbers are irrational. In fact, if you choose a random real number, there is a 0% chance that it'll be rational. I know, it's a little weird. So in any case, though, okay, we can find the slope of this tangent line. Now, if we wanted, we could then find the equation of the tangent line. How would we find the equation of the tangent line?
What do you mean next to the original formula? And then doing the slope form.
Yeah. All right. If we plug x into this formula, right, so if we look at what is y at 1, y at 1 is 3 minus 1 is 2 over 2 plus 4 is 6, so it's a third. Okay. So the point that it hits the curve is 1 comma a third. So the equation of the tangent line is, well, you can do y minus a third equals 7/12, that's our slope, times x minus 1. Or if you like, y equals 7/12 x. We'll see, it's going to be a third minus 7/12. And we saw yesterday how to do this. It's going to be 12 minus 21, which is minus 9 over 36, which is minus 1 over 4. So there's the equation of the tangent line, the curve. Which, again, it's actually a little bit remarkable that you get such an easy, I mean, I put this function out more or less randomly, other than the fact that I used reasonably nice numbers and I chose x equal to 1. So in any case, that's not so bad. Okay.